Today we will be looking at dark energy, the mysterious force that is making the universe expand, and I'm going to try to clear up some of the confusion on this topic. A few weeks back we looked at dark matter, and I pointed out there that dark matter and dark energy have few things in common. One is that they have the word dark in them, another is that they make up most of the matter and energy in the universe, and a third is that we do not know much about either, part of why they are called dark. This is especially true of dark energy, about which we know very little, but we have not been studying it as long. We do not know much about it, but at the same time, it is not that mysterious, and we might as well start at the beginning, since that was a bit under 20 years ago. Now, to be fair, some of the concepts used in and around dark energy are older than that, but dark energy as a term popped up when I was in college. Michael Turner coined the term in 1998 when I was 17 and just starting my junior year in college, but I don't recall hearing the term for another year or so when I attended a colloquium on it, and at that time the interest was all in supernova and whether the universe was going to expand or collapse. It was just getting hinted at that accelerating expansion might be on the table, and all those options were inside the margins of error. At least as I recall. To be honest, I mostly sat through the weekly departmental colloquiums for the free coffee and cookies those days. I was very much a novice in my studies, and the topics were pretty over my head. In any event, the focus at that time was on supernovae, and at that time we actually had not detected many, which was why the margins of error were so large on cosmological expansion back then. Some of you might recall that Robert Evans, a minister from Australia who was an amateur astronomer, had amazed everyone with discovering tons of them by direct visual observation, over 40, and for a while in the mid-90s a sizable fraction of the supernovae we knew of were his discoveries, so not a big sample. Now why does that matter? Supernovae come from multiple sources. Most people are familiar with it as an old giant star exploding, but a Type 1a supernova is one that occurs when a binary star system, with one of the stars having already died and turned into a white dwarf star, begins sucking up matter from its neighbor. Once that white dwarf sucks up enough matter to become about 1.5 times more massive than our own sun, it explodes as a supernova. There is a maximum amount of mass a white dwarf can have. This varies a bit on its composition and spin rate, but once it hits that mass limit, it will erupt as a supernova. This tends to release about the same amount of energy each time, about 1 to 2 times 10 to the 44th joules, and with similar spectral characteristics, so it makes an excellent standard candle. That being an object that we can look at and say, this must be such and such a distance away, with such and such a redshift, and therefore speed away from us. Now, no two supernovae are exactly the same, but these white dwarf stars exploding as supernovae is a fairly small window, and of course they are quite bright so we can see them billions of light years off. This is not a video on supernova, but as a fun fact, the classification system for supernova, sometimes called the Minkowski-Zwicky system, takes that name from astronomer Rudolf Minkowski, who was the nephew of Hermann Minkowski, one of Einstein's teachers, and the same Fritz Zwicky who coined the term dark matter and the term supernova, and found around 120 of them himself, a record only surpassed about 7 years ago. In any event, as we catalogued more and more of these standard candles, it began getting pretty obvious that the expansion of the universe was not slowing down. We would expect that it would, as gravity began pulling things back together. What we saw instead was that it was speeding up. How do we know this? Redshift is how much light shifts to longer wavelengths based on how fast the object is moving away from us. Everything in the universe besides our galaxy and its nearest neighbors is redshifting away from us, meaning it is moving away from us. And that is how we got the notion that the universe is expanding, and presumably once was smaller, from whence comes the Big Bang Theory. The further away something is, the more redshifted it is, meaning the faster it is moving away. The further out in space you look, the more redshifted stuff is. We can also pin down the distance to a Type 1 supernova quite well because they all tend to be about as bright. So you can calculate how far away they are based on how much fainter they are. This is the same as if I told you passing airplanes all had 1000 watt light bulbs on them for navigational lights. You could figure out how far away they were by how much dimmer those lights were, and from that determine their speed, simply from knowing how bright those navigational lights were. But you would also have some uncertainty because not every bulb would be exactly the same brightness. Different manufacturers, ages on the lights making them dimmer, dust and grime over the transparent plate covering the bulb, that sort of thing. Those would all limit how precise you could be regardless of how accurate your own equipment was, and the same is true of Type 1a supernova. So we cannot be too precise with each individual supernova, but as we measured more and more of them, we could get an increasingly accurate picture. I want to stress that because once the effect got noticed, it took some years of observation to shrink the margin of uncertainty down enough to be sure. As I mentioned when I first heard of it in a colloquium right around the turn of the century, those uncertainties were still high enough, it looked likely, but hardly certain, the rate of the universe expanding was faster and faster. If the universe's expansion was constant, we would expect an object to be at one spot, whereas if it was getting faster, then it would have been slower in the past, closer than the constant expansion would produce, while if gravity was slowing the expansion down, it would have been faster in the past, and the object further away than you would expect. As you know, it turned out to be the former, that the expansion is increasing in speed. But I wanted to cover that because people tend to skip it when talking about dark energy. There is other evidence for dark energy, but that was the big one that established that the universe was expanding at an accelerating rate. We will skip detailing those other methods. They are handy for an alternative proof or refining our figures, but supernova is how we determined it, and also I think the most conceptually simple approach. The others all require a discussion of topics that would need whole episodes to themselves, which we might do someday. Now you might be asking, what does the universe expanding have to do with dark energy? Well, it takes energy to make the universe expand faster and faster, and we call that energy dark energy. It is the energy expanding the universe. Or at least it probably takes energy, so it is called dark energy, rather than just that weird thing making the universe expand, which energy would seem to be the best candidate for. Matter pulls on other matter by gravity, so on first inspection, you would expect things moving away from us to start slowing down. As we just covered, that is what we expected to find with the supernova measurements and did not get. For this not to be happening, it takes some force or energy. Now what is strange about this is that it isn't getting diluted as space expands. Everything else does. Gravity keeps our galaxy together and bound to our nearest neighbors, so our density has not particularly changed with time, but the overall density of the universe is constantly decreasing as space expands. Same stuff, more space, lower density. But not dark energy. That seems to be constant at a bit less than a billionth of a joule per cubic meter. That might not sound like much, but it means a cubic light year has more energy in it than all the energy the sun has emitted during human history. It is a lot of energy, and it is everywhere. Every cubic light year, be it in our solar system, or outside our galaxy, or even those giant voids, which actually are not that empty of normal matter either. Voids are a topic for another time too, but they are one of the other evidences for dark energy. And it is not like normal matter that likes to clump together into stars and planets and people, or like dark matter, which as we discussed last time at least tends to clump up at the galactic scale. It is everywhere, evenly spread. Now that should be tripping some alarm bells in your head, because I just said it is like that everywhere and not getting diluted, while the universe is expanding. Same density of energy, even while the universe gets bigger, and that means more energy. If I expand the Earth, we would expect its density to decrease. If it is not, it is getting matter from somewhere. If I am expanding the universe, and it is keeping the same energy density while I do that, I am getting new energy from somewhere. That would seem to be a blatant violation of conservation of energy, one of the most bedrock laws of science. And it might well be, but energy is a pretty ill-defined concept in general relativity. Probably not too surprising since the unit of energy, the joule, is made up of the units for mass, space, and time, which you know also act weird in general relativity. You can read some wonderful arguments about whether or not we should say energy is conserved in general relativity or dark energy, but it is important to emphasize, I think, that they are actually arguments over whether or not we should say it is. The argument is not really about what is going on, but how to phrase it to folks who are not physicists or mathematicians. I, personally, tend to agree with cosmologist Sean Carroll that it is just easier to say that energy is not conserved when space-time is changing. This seems intuitively straightforward then in this case. As the universe ages and pumps out more and more brand new space from seemingly nowhere, this new space brings energy with it. We do not know where dark energy or this new space comes from, but if you wanted to think of it as leaking in from somewhere else, I would not say that was wrong. It also rather neatly circumvents the whole conservation issue anyway, since we already know no system is being conserved when it is not closed because something is pumping more stuff into it from the outside. I will include a blog post from Sean Carroll discussing this conservation of energy issue in more detail in the episode's description. On a last note on that aspect of things though, if we do have space and energy leaking from elsewhere, that makes folks wonder what that place would be. Indeed, dark energy does often come up in regards to the higher dimensional aspects of string theory, or in the idea of multiverses, or the fine-tuning argument in general. However, I like to remind people that we already had this problem with the Big Bang itself, with space, time, and energy just coming out of nowhere. So I do not consider it strong evidence for any of those. I just do not think we know enough yet to speculate in that regard. Speculation is always good, but such things tend to be impossible to experimentally verify, so to me they are places you go when you exhaust all other alternatives. One of the popular ideas though is that there is an energy cost for space to exist, so that dark energy is constant everywhere and evenly distributed in space because it is the actual energy of space. It is kind of like saying that water is evenly distributed throughout the ocean. You can dump more water in the ocean, but any given bit of it will have the same amount of water as another. Water, like most liquids, is incompressible, or very nearly so. That is how hydraulics works. A kilogram of water takes up a liter of space, or 1 gram per cubic centimeter, whether it is at the bottom of the ocean or the top. Dark energy appears to be a lot like that. It is just the basic minimum energy needed for the space to exist, or the minimum energy a space will have, perhaps. It takes a gram of water, or 9 times 10 to the 13th joules of energy, to make a cubic centimeter of ocean exist, while it takes about 10 to the negative 29th grams of matter, or 10 to the negative 15 joules, a femtojoule, to make a cubic centimeter of space exist. And again, space and time and energy are all pretty thoroughly connected at a fundamental level. That is not exactly new and deep thinking. So if you have more space, from the universe expanding, it is not a big leap to assume there was energy connected to doing that. One of the big candidates for dark energy is a familiar term, vacuum energy, and it is more or less the same concept as zero-point energy, a popular one in science fiction. Like I mentioned, there is not much dark energy in a tiny bit of space, but there is an awful lot of space, so it adds up. Tapping that for power is, of course, incredibly tempting and has become a common theme in sci-fi. I have never personally heard a good scheme for how you could do this, and I tend to be of the opinion that you cannot. Hypothetically, if you could suck in a chunk of space, leaving it missing, you maybe would get some energy from doing that. But how you do that is a complete mystery to me. Anyway, vacuum energy is full of all sorts of virtual particles constantly popping in and out of existence, or some sort of existence anyway. We talked about those some episodes back when discussing them and micro black holes and Hawking radiation. Zero-point energy itself is the lowest possible energy that a quantum mechanical physical system may have. Essentially that even if I took a box full of particles and reduced it to absolute zero, it would still have some energy. Now, to the best of our knowledge, you cannot reduce anything to absolute zero, but even if you could, it would still have this 0-point energy left over. This is the energy that is still there even after you have extracted everything else, so it is sort of counterintuitive how you will get more energy out of it. I would say the key thing to take out of that, though, is that any given volume of space has energy associated to it, even if it is empty of normal matter and does not have photons passing through it. This does bring up the vacuum catastrophe, though, because when we calculate the amount of energy quantum field theory tells us should be in any given chunk of space, we get one value, but when we check that experimentally, this energy should exert gravity after all, we get nothing like that. As I mentioned earlier, when we calculate this energy based off the gravity it should be exerting, we come up with something like a billionth of a joule per cubic meter or less. This is what we get from observing the universe. But when we run the numbers that quantum field theory offers us, by looking at the subatomic scale rather than the intergalactic scale, the values it gives us are not tiny fractions of a joule per cubic meter, but more than the entire mass energy of the universe squeezed into a spot smaller than a single proton. You can see why this is called the vacuum catastrophe, or the worst prediction in the history of physics. I will attach an article by theorist Matt Strassler in the episode description if you want a good walkthrough of this and 0-point energy in general, with a minimum of math. Okay, so the idea that dark energy is just the energy of space is a pretty popular one right now, but the evidence is hardly conclusive and there are lots of other candidates. I want to cover a few more, and also hit on some of the terms you will encounter a lot if you explore this more on your own, which I hope you will, as it is one of the greatest mysteries of modern times. Another popular idea is that dark energy is not energy at all, but just evidence of our understanding of gravity needing some work, which is certainly true. While gravity was the first of the physical forces we discovered, it remains arguably the worst understood one. We know that gravity falls off as an inverse square to distance. Double your distance, quarter the force of gravity, get 10 times further away, and it is 100 times weaker. But we cannot actually be sure it precisely follows that law, even at huge distances. And as I mentioned in the dark matter episode, the idea that it might get weaker at the intergalactic scale was one of the more popular explanations for dark matter, though most evidence these days strongly points against that. We also cannot rule out that gravity is repulsive at cosmic scales. Gravity is the only one of the forces with no repulsive aspect, it just attracts, and is way weaker than the other forces, electromagnetic and the weak and strong nuclear forces. To the best of our knowledge, it is strictly attractive, and has no repulsive aspect like the other forces do. However, it could have a repulsive aspect at the extreme scale that results in this expansion of the universe. As you get further away, gravity gets weaker, and if there was a repulsive force that began to get stronger as you got more distant, millions of light years or more, you would get to a point where gravity becomes a net repulsive force. Of course, if that repulsive aspect did begin to dominate over the attractive aspect at large distances, you would expect that to mean that as the universe got bigger and bigger, the repulsive aspect would get stronger and stronger, causing an accelerating expansion. There is absolutely no proof of this, but there is basically no proof of much of anything to do with dark energy anyway. To get to our next one, I think I should go ahead and introduce the cosmological constant. You will see this along with the lambda CDM model a lot in discussion of it, and it can get needlessly confusing. We use the Greek letter lambda for the cosmological constant, and CDM is short for cold dark matter. So the lambda CDM model is just the one where the cosmological constant is being used for dark energy, and we assume dark matter is cold. We discussed why temperature matters in the dark matter episode. It is not the consensus cosmological theory. There really is not one, and we just don't know enough yet to have one. But it tends to be the default one that others get compared to, that this is a cosmological constant and that dark matter is real and cold, which is to say, made of particles that do not move at high velocities compared to most matter we see spinning around the galaxy. The cosmological constant is the energy density of the vacuum of space, or how much energy a given chunk of empty space has. We already talked about vacuum energy, and this is essentially that, and you often see a version of this expressed as omega lambda, which is just the ratio of the cosmological constant to the critical density of the universe. The critical density of the universe is defined as the density the universe would need to be to make the universe eventually stop expanding. Rather than constantly expressing that as something like 10 protons per cubic meter, we just say that when omega is exactly equal to 1, the universe would eventually stop expanding and stay that size. If it is above 1, it would collapse back in on itself, the Big Crunch. And if it is less than 1, it would expand forever. I assume omega was picked because of it being the last letter of the alphabet, and those connotations of it spelling out the end of the universe and such. Omega itself would have to be equal to 1, and it is actually the sum of 3 terms: omega mass, for classic matter and dark matter, omega relativistic, for photons and neutrinos, and omega lambda for the dark energy component, where dark energy is the cosmological constant, or the vacuum energy of space. Omega lambda is currently estimated to be about 0.69. We also have the notion that dark energy might be some fifth fundamental force and energy, quintessence. There is more than one version of this, but the general notion is that the force driving the universe apart can change with where and when you are. This is a nice one since it predicts noticeably different results than the cosmological constant does, so we should be able to say which one it is as we gather more data. Current evidence is not in favor of quintessence, but has not ruled it out either, so it deserves a mention. Now there are tons more options, but those are the only ones I think we have time for today. Others are either a little too difficult to explain briefly, or maybe a bit too out there. They might be right, of course, but our goal today was not really to explain dark energy, we can't yet, but to acquaint ourselves with why we think it exists, and the more common terms and concepts mentioned in regard to it. One last common thought is using dark energy as a power source, as it is most of the energy in the universe and seems to be increasing to boot. It would, without a doubt, be an amazing power source if we could harness it. Better yet, since it seems to be the very energy of space, if you could, for instance, suck chunks of space up for their energy, that would make a pretty awesome spaceship. You could potentially suck up some of the space in front of you, shortening the way to your destination, much like the Alcubierre warp drive we have discussed before. The one commonly suggested method would be to take a rope wrapped around an axle attached to an electric generator and tie one into a spaceship that goes and tows it many millions of light years away. Obviously, this would have to be an impossibly sturdy rope. Once the end is that far away, dark energy should be strong enough to keep pulling it away faster and faster, turning the generator. You would also have to swap a new one in from time to time, tying the new rope to the end of the old one. Ignoring for the moment that rope would need to be impossibly strong, I cannot personally think of any reason why this would not work, which does not mean it would. I am no cosmologist or general relativity expert. Also, I would not be surprised if it turned out the mass energy of the rope turned out to exceed the energy you would gain from this. To the best of my knowledge, though, this method would work, on paper at least. To seriously speculate about how to use it for power, we need to understand how it works, and we just do not know yet. It is undeniably mysterious stuff, one that may take generations to figure out. But hopefully by now, you have a more down-to-earth view of what it might be and why cosmologists feel so confident it exists, and it is not just some crazy idea that came out of nowhere. I try to keep the content on the channel as down-to-earth as I can, after all. Speaking of which, next week we will look at how to destroy the sun. And I will actually be trying to explain how we can remove matter from stars, called star lifting, why this might be quite down-to-earth and practical, and why we might do this to get a useful source of matter to build stuff with, and to extend the star's lifetime. We will cover some of the ways this could be done, and what you might be able to do with all that matter. This was the second winner of our Patreon topic contest, and we have one more which I will be picking before the next episode comes out, so the deadline to enter topics for it is Saturday, October 2nd, 2016. so you can still submit topics until then. The week after that, we will look at cryptocurrency and blockchain, doing both a basic introduction and looking at some interesting applications it might have in the future, along with some of the pros and cons of such things. That will get followed up on October 20th with an in-depth look at the Kardashev scale and what some of the capabilities and traits of such civilizations would be. Nothing is determined for after that just yet. Over at the Facebook group, Science and Futurism with Isaac Arthur, we have an ongoing poll of topics, and that is where most of the videos in November will be getting picked from, so you might want to head over there and vote for the topics you like, or add new ones. So again, next week is Starlifting. Don't forget to subscribe to the channel if you want alerts when that and future videos come out. And in the meantime, you can try out some of the other episodes on the channel. If you enjoyed this episode, don't forget to like it and share it with others. Until next week, thanks for watching and have a great day.